Jai Hind. Myself Nidhi Singh, Assistant Professor in Akgec Engineering College. So I am going to discuss the solution of AKTU question paper for the subject BW101, that is Fundamentals of Electrical Engineering. And in this part, we are going to discuss the section C question, that is question number 5th. The previous questions can be referred in the previous series. So the question number 5th is a 20 kVA 200 volt by 2000 volt by 200 volt single phase 50 Hz transformer has a primary resistance of 1.5 ohm and reactance of 2 ohm. The secondary resistance and reactance are 0.015 ohm and 0.02 ohm respectively. The no load current of transformer is 1 ampere at 0.2 power factor. So here we have to determine equivalent resistance and reactance referred to primary, and in second part we have to find total copper loss. And in the same question, part B is you have to draw phasor diagram of ideal and practical transformer at no load condition. So first we will, so out of these two, A and B, you can attempt any one question. So first we will solve part A. So first we will write the given values, right? So given values, the rating is given for transformer. The rating is given 20 kVA. 20 kVA rating is given. The ratio is given 2000 volt by 200 volt. These are the given values, right? These are the given values. Then this is always given primary to secondary ratio, right? So, and frequency is 50 Hz, has a primary resistance. Primary resistance means R1 is given 1.4 ohm and reactance is given 2 ohm, right? So, these are the primary resistance and reactance which is given in the question. Then secondary resistance is given, R2 is given 0.015 ohm and X2 is given 0.02 ohm. And no load current means I0 is given 1 ampere and power factor cos phi is given 0.2. Now what you have to determine? You have to determine equivalent resistance and reactance referred to primary side. It means you have to find, these are the given value. So now you have to find R1E and you have to find X1E, right? So R1E, what is the formula for R1E? R1E is equal to R1 plus R2 dash, or you can write R1 plus R2 by K square, right? And similarly, you can find X1 is equal to X1 plus X2 dash. This is the secondary value which is transferred to the primary, or we can say referred to the primary. So this can be written as X1 plus, so when secondary values is referred to primary side, it gets divided by K square, right? So you will write X2 by K square. Now what is this K? K is N2 by N1 and you can write it as V2 by V1. So what is V2 given here? V2 is given 200. So this is 200, and what is V1 given? V1 is 2000, right? So 2000. So you will cut, this will be equal to 1 by 10, or you can write 0.1. So K value is 0.1, right? So by putting all the value of R1, R2 dash, you can find out the value. So R1E, what is value? R1 value is given 1.5 plus, what is R2 value is given? 0.015 and K we have find out 0.1 whole square, right? And you can, after solving this, you will get the value of R1E. Similarly, X1E, what is value of X1? X1 is given 2 ohm. Right, plus what is X2 is given? X2 value is 0.02 divided by 0.1 whole square. So you will get value of X1e. So you can find value of R1e, you can find value of X1e. Now next you have to find the total copper loss, right? So total copper loss, now what is the total copper loss? Let me raise this first. Okay, so now, okay, total copper loss. So total copper loss you can find by I1 square R1 plus I2 square R2, as R1 value is also given, R2 value is also given, and you can find value of I1 and I2. Or you can also find it as I1 square R1e, because you have already calculated the value of R1e. So you can also use this formula I1 square R1e. So R1e you have already find out what is R1e, right? Now now only you have to find the value of I1. So how will you find value of I1? I1 will be is equal to kVA rating. So what is kVA rating given? 20 kVA, right? So 20 kVA into 1000 divided by V1. So V1 is given 2000, right? So you will get the value of I1. So I1 square R1V, if you solve this, you will get value of copper loss. So we will see what are the answers. So R01, this is coming 3 ohm, X is coming 4 ohm, right? So these are this is basically R1E and this is X1E, what I have referred. So R1E, X1E. So this is 3 ohm and 4 ohm. The answer is 3 ohm and 4 ohm. And the I1 value is coming 10 ampere, right? It is 10 ampere. So copper loss will be equal to 3000 watt. Because so you are finding by I1 square R1E and this value is 10. So 10 square into 3. So this will be 300 watts. So this is the required answer, right? Okay. Now the next, draw the phasor diagram of ideal and practical transformer at no load condition. So at no load condition, you have to draw the phasor diagram for ideal transformer also and for the practical transformer also. So whenever we draw the phasor diagram, first we take the reference line. So in case of transformer, we will take flux as a reference line because flux is same for the primary side also and for the secondary side also. So generally we take that parameter as a reference, which is common for whole circuit. So phi is common for the whole circuit. So we will take phi as a reference line, and with this phi we know the relation of the induced EMF, that is E1 and E2. So when we have derived the EMF equation of a transformer, we have seen that the E1 and E2, they lag flux by 90 degree, right? So lagging means you will draw downward side and by 90 degree. One second. Okay. So now you will draw E1 and E2. So they are lagging phi with 90 degree, right? So this will be at 90 degree. Okay. Okay. Now we have drawn E1 and E2. Now if you see for the ideal transformer, right? So in ideal transformer, here the current is the no load current, which is coming I0. No load current is I0, which is going here. And as there is no losses in the transformer, it means the whole current is magnetizing the core. So we also denote this current as equal to Im. Why? Because the whole current is magnetizing the core, there are no losses. So in ideal condition, we know that all the losses like core losses or copper losses and the leakage flux, we consider that all these things are 0. So it means the whole current is magnetizing the core. So we refer it as the Im. So here we are applying the voltage V1 and we are getting V2, and the induced EMF is E1 and E2. As there is no loss, so this E2 will be equal to V2 because there is no loss in between. So we can write E1 is equal to V2, right? Now we have already drawn E1, E2, V2. We have plotted this, and now what about this V1? So this E1 will always oppose its cause. So what is the cause of this E1? The cause of this E1 is V1. Because of this V1, it is getting produced. So this E1 will oppose its cause. So E1 is here, it will oppose its cause means you will draw V1 opposite to this. So now this is V1. Now you have to draw IM. So as IM is the magnetizing current, and this is basically now as we are considering for the ideal transformer. So it means it is magnetizing. So in case of purely inductive, we know that the relation between V and I means current will lag V by the 90 degree. Or we can say because of this phi, this IM is producing. So phi and IM will be in the same phase. So you will draw this IM in same phase with the phi, right? So this is the complete phasor diagram for the ideal transformer. So where you can write this phi is flux, IM is magnetizing current, right? Then E1 and E2, they are the induced EMF of primary and secondary side, right? And V1 is the supply voltage. So these are the parameters. Now coming to the practical transformer, right? Now you have to draw the phasor diagram for the practical transformer. So for practical transformer, at no load condition, means at secondary side, current at secondary side, so here we have V1, no load current is I0, as there is no load as a secondary side, so I2, there will be no I2. Here we have E1, here we have E2, there will be no current and V2, right? Okay. Now we have to represent all these things in the phasor diagram. So again we will take the reference phi, right? And we will now draw. Now we know the relation of E1 and E2 with the phi. It is lagging phi by 90 degrees. So we will draw E1 and E2 here, and by showing it is lagging by 90 degree. We know that V1 will be in the opposite direction, right? Now what about this I0? Now in this case, this is not the ideal transformer, means there are some losses. So now this I0 has two components. I0 is equal to IM plus IC, right? So this I0 has a two component, and IM is called the reactive component. This is called the reactive component, and this is called the active component, or we can say the loss component, okay? Because now in the practical transformer, there are some losses. All the current is not magnetizing the core. So this is the loss component, okay? So now we have to, so if we add these two current, we get the resultant I0. So first IM, we know that IM will be in the same phase with phi. And now as this IC is the loss component, so losses happens in the resistance. So in resistance V and I, they both are in the same phase. So we can draw this in same phase with the V1. So IC will be here. So now we have to draw the resultant. So to draw the resultant, draw the line which should be parallel to this line. And from here we will draw the line which should be parallel to this line, right? And we will join this origin and the intersecting point here. So this current is I0, right? And the angle between I0 and V1 will be phi naught. Okay. So what are the different parameters here? So as phi, all these parameters are same. The extra parameters are the I naught. I naught is called no load primary current, right? No load primary current. IC is called, as I have already written, this is active component, and IM is reactive component, or we can also call it as a loss component. Okay. And what else? The phi naught. So this phi naught is no load power factor angle. Okay, this phi naught is called no load power factor angle. So this is how you can draw the phasor diagram, right? So this is the required answer for this question. Now we will go for the next question. So here you have to derive the expression of torque for DC motor, and after this the numerical is there. So first we will see the torque equation of a DC motor. Okay. So here we are supposing that this TA is the torque developed and in Newton meter by the motor armature, which is running at n RPM, that is rotation per minute. So work done will be TA into 2 pi n watt. So now the same electrical equivalent of the mechanical power which is developed by the armature will be equal to EBIA, right? This is the electrical equivalent of the mechanical power which is being developed by the armature. So if you equate these two equations, equation 1 and equation 2, if you are going to equate these two equations, here you will get T is equal to 2 pi n by 60 is equal to EB into IA, and now TA is equal to EBIA 2 pi n by 60, and we know that EB, which is back EMF, and which is the EMF produced in the armature, and we know that this is equal to 5 Pn Z upon 60A, right, which is written here. So we will put this value in this equation. So after placing this EB value in this equation and solving, you will get TA is equal to Z 5P by 2 pi into IA upon A, and this, all these are the constant values, right? So if you solve this, you will get this, the required torque equation for the DC motor. Now coming to the numerical part. So the question is, a 6-pole lap wound DC shunt motor has 500 conductors in the armature. The resistance of the armature path is 0.05 ohm. The resistance of the shunt field is 25 ohm. Find the speed of the motor when it takes 120 ampere from DC mains of 100 volt. Flux per pole is 0.02 Weber. So first we will draw, this is for the DC shunt motor. So first we will draw the DC shunt motor. Right. So here in DC shunt motor, back EMF is there, IL is coming from here, and the DC main is given 100 volt, right, and current will go in the armature. This is IA, in the, this is shunt, so ISH, the resistance of this is RSH. Okay. Now we will see what are the given values. This is the 6-pole, number of pole is given 6, and this is the lap wound. So in lap wound we know that number of parallel path is equal to number of pole, and the shunt motor has 500 conductors. It means Z is equal to 500. The resistance of armature path, it means RA is given 0.05 ohm, and the resistance of the shunt field means RSH is given 25 ohm. Find the speed of the motor when it takes 120 ampere, it means IL is given 120 ampere, right? And you have to find N, speed of motor. So how will you find? So first we will see what how we can find the speed, in which formula there is a relation for the N. So we know that back EMF is equal to phi P N Z upon 60A. So by using this formula, we can find the value of N. So first we will see what are the given values for this, for solving this equation, right? So phi is given, I suppose we have not written the value of phi. Phi is given 0.02 Weber, right? So phi is given, right? Number of pole is given, and you have to find Z is given, that is number of conductor. You know that A is equal to P because this is lap count, but EB is not given, right? And you have to find, and EB is also not given. So how you will find the value of EB? So EB value can be found by this DC shunt motor circuit. So if for this equation we know that V is equal to EB plus IA RA, right? So from this equation we can find the value of EB. So EB is equal to V minus IA RA. We know the value of V, we know the value of RA, but we don't know the value of IA. So how will you find the value of IA? Now first we will see the current relation. So IL is equal to IA plus ISH, right? IL value is given. What is given IL? This is 120. IA is not given. We will find by using this equation. What is value of ISH? ISH can be found as ISH is equal to V upon RSH. So V is given 100 and RSH is given 25 ohm. So divide by 25. So this is equal to 4 ampere, right? So this is 4. So IA is equal to 120 minus 4. So this is equal to 116 ampere. So by putting all these value, we can find value of EB. So EB is equal to 100 minus IA is 116 into, and RA is 0.05, right? So after solving this, we can find the value of EB, and after finding the value of EB, you can put this value in this equation and you can find the value of this N. It means the speed of the motor, right? So you can find EB is 94.2 volt, and if you put this, you will get speed is 565.2 RPM, right? Or you can round it off 565 RPM. So this is the required answer. So this is all in this lecture. The remaining questions we will discuss in the next lecture. Jai Hind. Thank you.